Welcome to Automatic's Dev AI NYC gathering. We're thrilled to have such an incredible group of people here. While you're here, if you want to meet some folks from Automatic, I'm going to point out a few. There's more than just a few, but M. Shreve from our AI team, Jesse Friedman, who leads WP Cloud, and Nacho Iglesias. If you are a person who's interested in AI and analytics, there's your person. They're here with a bunch of other automaticians who will be thrilled to talk to you afterwards. It's a privilege to bring together two people who have shaped the way that we build and we think online. Stephen Wolfram is a pioneer in computational thinking, the creator of Mathematica and Wolfram Alpha. He's a longtime force behind how we use computation to model knowledge and explore complexity. He's also an advisor to Automattic, where many of us have benefited from his perspective, and tonight you will too. Matt Mullenweg is the CEO, founder of Automattic, and he's also the co-founder of WordPress. He's spent over 2 decades democratizing publishing, commerce, messaging. Matt stewards one of the largest open source communities and champions the idea that software should be open and accessible. Tonight, they're going to explore how computation shapes creativity and what the future of the web looks like as open systems evolve and shape how we live and how we work. Please join me in welcoming Stephen Wolfram and Matt Mullenweg.
Thanks.
Wow.
I have to have my laptop safety blanket here. If you need to use it.
We might pull it up, you know, in case we need to. So, Stephen, you have had the privilege of working with like some great people, like Richard Feynman. What do you think he would think of what's happening right now with this LLM?
He would say, how do these things work? Because his big thing was, you know, given some general area, just like kind of try and drill down, find out what the sort of essence of what's going on is. And I suspect he would be doing something that I've also been doing a bit of, which is trying to understand sort of what is the foundational science of what on earth is going on in an LLM. I think that's one of the things. In terms of you know, okay, so I'll tell a little bit of a funny Feynman-related story. That a recent thing done by some people I know at Harvard, they were working out some Feynman diagrams. So in particle physics, one of Dick Feynman's contributions was these things called Feynman diagrams, which are a way to work out, you know, interactions of particles. That was sort of one of his achievements. So there was a thing recently of, oh, you can use, you know, an LLM to help you figure out more stuff about Five-Gluon interactions. Okay, actually you could use our technology, Wolfram language and so on to do that too. And it turns out that I learned that the people who've been working on that were checking everything they were doing with our tech. So, but the thing that I realized is they just worked out this Five-Gluon thing. I realized when I was a 17-year-old kid, I worked out the Two-Gluon case back in 1977. It was actually the first place I had used computers to do sort of production grade mathematics for physics. Mm-hmm. So that was that's a small kind of a thing that happened recently that was kind of bringing together sort of ancient history for me and modern LLM stuff. And you know, these Feynman diagrams, I don't know if people here know about them, but they're this way that's used to calculate things in particle physics, and they're really difficult to calculate. And Dick Feynman was always saying, you know, they're really a silly way to calculate these things. There's got to be a better way. Now LLMs can help a little bit in doing these things.
That's so you've had quite a journey. Who here is familiar with Wolfram's sort of history and everything? Like, raise your hand. So you've been a remote CEO,
yes,
longer than I have. 40 years or something, right?
Yeah, not quite. 1991.
1991, yeah. So I was what, 7 years old or something. You also have recorded every keystroke everything? Like, tell us a little bit about that.
Yeah, I mean, I'm just a person who likes data, so I've collected lots of it about myself. Occasionally it's useful. Certainly having an email archive that goes back 40 years is really useful, because lots of things, a lot of projects that I do are things that I actually started decades ago, and for some reason or another I couldn't make progress on them. And then, the world changes and progress is possible. I mean, and sometimes these projects are things like, I was interested in neural nets back in the beginning of the 1980s and didn't manage to get them to do anything very interesting. And then eventually that turns out to be something where exciting things happen. I was just working on things about biological evolution, which turns out to be closely related to the foundations of how neural nets work. I tried to do it in the mid-1980s, it didn't work. I basically got back out the same things that I worked out at that time and now managed to make them work recently. So it's really useful to have this sort of long archive of what one's tried to do.
You mentioned to me, what's it feel like to have things that you've been working on for decades now finally starting to hit?
Yes, well,
like what's an example of one?
Oh, I don't know. I mean, a lot of stuff we've done. Okay, so in science, I do two kinds of things. I do a bunch of technology and I do a bunch of basic science. And right now happens to be a time when both a bunch of technology things that I've done for a long time are suddenly of significant interest, and also a bunch of things have happened in basic science that suddenly have been big breakthroughs. So it's kind of keeps me really busy. But let's see, in terms of science, gosh, things about fundamental physics that I've been sort of working on for a long time. I think we now can claim that we understand kind of what at least the machine code level of how the universe works, what that is, which is kind of exciting. And it's sort of the result of things that I did starting in the beginning of the 1980s and so on. And finally, in 2019, that was sort of a big breakthrough in that kind of the formalization of things. But you can think about things just talking about them in ordinary natural language, for example, but sort of the big kind of the ability to have a more formal statement about what's going on is what's led to a lot of the development of technology and science and so on. The big example of that is mathematics, where you can kind of formalize things about the world and build this kind of big tower of consequences. And the thing that I think is the thing of our time is kind of using computation as a broader sort of way of formalizing things than mathematics has been, and building this kind of big tower of consequences of thinking about things in computational terms. And sort of a big effort of my life has been providing, in a sense, the notation for thinking about things computationally. I mean, back in the day, people went from talking about mathematics in terms of words to having a notation like plus signs and equal signs and things like this. And that's what sort of launched algebra and calculus and eventually all the mathematical sciences. And kind of my effort has been to sort of build a computational language that provides a notation for thinking about things computationally. And that's a thing that has been, I would say, increasingly valuable. And now we can see, LLMs do the thing that we humans had been able to do before, of just sort of talking about things in terms of words and so on. But they too benefit from this kind of formalization and this ability to kind of make a sort of structured tower of consequences. And that's been an important sort of complement to what's happening with LLMs, is providing this kind of, I mean, I view there are foundation models. I view what we've tried to do with our computational language as providing sort of a foundation tool for foundation models, the sort of formalized version of what can happen, of how you talk about the world.
I want to go a little bit meta, because you are, how old are you now?
66.
66, and your output is increasing. You're one of my favorite bloggers. You have a great WordPress blog. Thank you. And so what is your, give me a day in the life of Steven. What's your productivity? Like, what allows you to be so productive in projects?
The meta thing is that I've spent years building tools to let me do stuff. So building technology tools, building organizations and so on, which allow me to sort of be as efficient as possible in going from an idea I have to sort of real sort of, actually implementing it. And I do work pretty hard too. Like I work all the time. So that helps. And I think—
How much do you sleep?
I sleep 8 hours. I lead a very boring life.
Do you nap?
No, not usually.
I'm a good napper. I napped right before this, actually.
That might have been a good thing. Yeah, it's no. I think I think the thing that has been really useful to me is figuring out the strategy for what to work on. And that's something people think, oh, you do the intellectual kinds of work and you do running companies kind of work, and those things seem very different. To me, they're actually very much aligned. That is, the things one needs to do, for example, in science, a lot of doing science well is not just knowing how to answer a question, it's knowing what questions are worth asking, which is really a strategy issue. And that's very similar to the kinds of things that one's confronted with all the time, in technology and companies and so on, is, okay, what's this, what strategy should we adopt? And I think, in my efforts CEOing, which I've been doing now for 40 years, it's, you're always having to make decisions about what to do. It's great practice for doing intellectual work and science and so on.
What's been most surprising to you? Because you run a very transparent life. Like you live stream many of your, we'll talk about this stuff. What things you live stream?
Right. I mean, about 8 years ago, I thought these software design reviews that we do within our company are fairly interesting. I think designing software, particularly designing the kind of computational language software that we do, it's a very intense intellectual activity. It's sort of the most difficult, the most concentrated intellectual effort that I know, because what you're trying to do is take all of these ideas and sort of drill down to the essence of those ideas to be able to know what are the primitives that we should implement in our language that capture all of these ideas. So I thought this is fairly interesting, and I thought maybe people out there in the world would find it interesting to see this stuff. And so we just started live streaming our design reviews, and that had many interesting features. I mean, first of all, when we actually had our act together to announce what topics we'd be talking about, we end up getting a bunch of sort of world experts in those things, logging in and giving us kind of real-time feedback on.
It's very much built in public,
yes.
like that.
Yeah. Yes, and I think, and then it's also a place where we find, people who are giving all kinds of interesting comments, and eventually we said, "Who are you? Would you like to come work for us?" That was one thing. Then when the pandemic started, I thought all these kids are out of school and so on. I should do a public service and do some kind of science and technology Q&A for kids and others. So I started doing that, and I found it really fun. I mean, I hope people find it interesting to watch. They seem to, but I found it really interesting. It's kind of a great, people ask this whole stream of bizarre questions, and I'm kind of, it's a great exercise. Just look at the camera and try and, without stopping, answer a bunch of questions. I found it's made me a significantly better explainer of scientific kinds of things. Plus, in my day where I'm doing a bunch of meetings, reviewing projects and things like this, it always improves my mood to do this, live stream Q&A thing, even when I've been kind of grinding, trying to get projects to happen and frustrated because things haven't gone as quickly as I would like and so on. You ask about productivity, I find that, I spend most evenings doing science, for example, and I'm kind of, it's always open, Wolfram notebook, and start sort of interacting with our computational language. That's my kind of medium for working out my thoughts. And I mean, I think for me right now, it's like people say, well, LLMs will write Wolfram language code fairly well at this point. It's not particularly useful for me to use them for that purpose, because I'm a fluent writer of our language, and I can typically know, I can start typing code before I could explain to anybody, including an LLM, what I want to do. So it's kind of that's a faster process. And I guess our language is sort of unique in that it's intended as a language for humans to think in, as well as a language that computers are supposed to implement. So that's, it's become an interesting thing because it's kind of like, it's sort of the unique thing. If you want to understand what you are computing, then our language is a good place to go. Even if you're using an LLM to sort of develop what you want to do, it's like you could just have the LLM write code that you're never going to look at. And that's fine if what you're trying to do is, lay out a dialog box or something and you can tell whether it got the right answer. But if you're trying to do some piece of science or something, you kind of want to know what computation was actually done. And so, we have this kind of unique situation of having a language which was intended for humans to read as well as humans to write and computers to interpret and so on.
What do you feel like the frontier labs are missing the most?
What are they missing the most? I don't know. It's been it's funny because, I know the leaders of most of them, and there's a sort of a slightly different set of understanding among the leaders and among the kind of the people in the middle, so to speak. I think, there's been a certain sense among the people in the middle, if we just train a bigger neural net, eventually everything will just, work inside the neural net. That's not, I think, correct.
So gradient descent is not all you need.
Yeah, I mean, the issue is there are things where, computation, there's a certain irreducibility to at least some kinds of computation that one wants to do.
So what's your take on the bitter lesson?
The what?
The bitter lesson.
Which bitter lesson?
Never mind then, if you don't know the reference.
No, I think the thing to understand is there's some computations where you just have to follow through each step to see what will happen. Okay, that's a phenomenon I happen to have studied a lot. Scientifically, I call it computational irreducibility, and it's a thing that happens all over the place. And when you have to just do all those computational steps to see what's going to happen, that's not a thing that you can expect a neural net to be good at doing. Because a neural net, you're feeding in, it's predict the next token, so to speak, and then ripple through the neural net, say what that token is. Okay, you loop back and you get to the next token and so on. It's, neural nets are good at broad but shallow computation. Not all computation is of that kind. And I think that's an example of something where, the idea that you should stuff into a neural net all the facts about the world and so on is kind of crazy. Knowing what the population of New York was in 1973 is not something that should be hidden in the, 8th decimal digit of such and such a weight inside the neural net. Not that it really is as simple as that.
So you're more on like is that the Hinton side of like thinking where neural nets are going to go, or like?
I haven't been I've known Jeff for a long time, but I don't know I don't know I can't claim to know.
Because it seems like the people just throwing CPUs at things are winning, right?
Well,
we're going to put data centers in space, and we're going to
Well, okay. I mean, look, the thing to understand is, okay, first of all, why do neural nets work? Why are they doing things which are useful to us? It's I think the number one reason is because neural nets are a bit similar to brains. In other words, if you just say, distinguish two images, which one is a cat, which one is a dog? You say, okay, there's a neural net that does a pretty good job at that. You say, well, what is it really doing? What is the mathematical definition of what a cat image should be versus a dog image? Nobody knows. The point is that in practice, neural nets do a job that we think is a good job because they more or less agree about what's a cat image and what's a dog image. And why is it that the way that they make these distinctions is similar to the way we make these distinctions? It's basically because their architecture seems to capture sort of essential features of how brains work. So things that brains are good at, neural nets, I think, have a fighting chance of being good at. Things that brains aren't really good at, like working out these sort of irreducible computations, there's no reason to expect that neural nets will be good at. And I think that that's that's an example. But you're asking what are these? I mean, just to say more quickly, I think one thing is neural nets don't do everything. They have to interact with tools. People are understanding that more and more. I think the big transition that's happened recently is going from kind of next token prediction to kind of more like next task prediction, where you're kind of doing these larger scale sort of what's the next tool I should call type things, rather than what's the next token I should write. And that's a so I think that's one thing. The other thing that's happened is the question of sort of the scientific foundations of LLMs and how neural nets work. That's surprisingly unresearched. I mean, in other words, it's sort of fallen.
Anthropic's doing some cool stuff there.
What's that?
Anthropic.
They are working on it. Yes, they have a serious effort there. I mean, I'm skeptical that the mechanistic interpretability story will end well.
Really?
I think the issue is because I don't think there's, okay, what do we mean by mechanistic interpretability? The thing that has happened, we've been on a run for the last 100 and something years, post-industrial revolution, that we think we can sort of understand the machines we're making. I don't think that is a continuing story. It wasn't a story, back in the day when people used donkeys to move things around, they kind of knew how donkeys worked operationally, but they didn't know sort of what was inside the donkey, so to speak. And, we've gone through a period when, yes, we understand the gears and levers and so on.
But your life's work is to understand this stuff.
Not quite. I mean, I think that it's okay. So the thing to realize is there's the question of does, are you building something which in the end, after all that neural net training, ends up with a bunch of cogs and levers that we can look at and say we know how the cogs and levers work? Okay, I don't think that's what's going on. I think a better analogy is, imagine that your objective is to build a wall, let's say. One method you can use to build a wall is you make bricks, and they're all very nicely shaped and so on. You build the wall up in this very engineering way. I think what's actually happening in machine learning is it's like you're building a stone wall, and there are a bunch of rocks lying around on the ground, and you notice, oh, this rock more or less fits in here, and this one fits in there, and pretty soon you've built a stone wall. But if you say, well, why is the stone wall? Why exactly does the stone wall have that shape in that place? There's no good answer to that question. I think that's, so I think, that will be a lot of what one will find. Now, the question is, are there kind of laws of LLMs? Just like in physics, you might say there's lots of microscopic things going on, they're very complicated, but there's some emergent law that's fairly simple to describe. What are the kind of laws of LLMs? And I think the bad case, okay, you can ask the same question for neuroscience. In neuroscience, you can say, what are sort of the general things we can say about brains? And you might be able to derive brain waves, okay? That would be a thing that is a sort of a feature of brains, a general feature of how brains work. It's not particularly useful if you want to understand how brains think. It's just and I think there are things like that we can find about LLMs. I don't think we're going to find this is the machine that the LLM is using inside. I mean, it's the same story with neuroscience, by the way. People look for kind of machines in brains, and beyond a few very simple things, they don't find very much.
Well, that brings us actually to a question from our mutual friend, Pablo Holman.
Yes.
He says, and then we're going to open this up for the audience as well. What do you think about post-LLM approaches to AI? Whether you think it's on track to advance truly advanced scientific discovery?
Post-LLM. I don't know what post-LLM is. Well, let's see. Matt warned me. He was going to take a few breaks here. So it's how do LLMs affect discovery in science? I think there are a few themes to that. One of them is LLMs are pretty good at doing sort of thematic searching of the scientific literature. People have studied lots of things in science, but the question is, can you put the pieces together to, make a new discovery, not by searching keywords, but by looking at sort of themes that have emerged? Can LLMs discover sort of grand analogies between one field and another? I'll give you an example of something I'm trying to do along those lines. So I mentioned, I think we've made great progress in understanding of the machine code of physics. The question is, what experimental implications are there to understanding that machine code of physics? So one of the features is we think that now that space is ultimately discrete. So we would like to find evidence for the discreteness of space. Well, people back in the 19th century were interested in, is matter discrete? Is it made of molecules or not? And people didn't know that until the end of the 19th century. Turns out there was an experiment that had been done in the 1820s by a botanist who discovered Brownian motion, a chap called Robert Brown. But that wasn't known to the people who were studying studying physics. And the question is, now in the situation that we have, trying to understand whether there's discreteness in space-time, can we do better now that there are LLMs? Could we discover that weird experiment that somebody did in some different field and realize that that's actually the thing that gives us the clue to show that, space-time is discrete or whatever else? The cautionary tale is that for 80 years of the 19th century, nobody knew that there was really good evidence that molecules exist. And I think this is a potential application for LLMs, is sort of this thematic searching of the scientific literature. Another example, one thing I've been chasing for decades is, can one make a universal constructor? Can one make something which out of molecules will assemble any molecule, any molecular structure one wants? Okay, that would be a big deal if one could find that. That would be kind of, the ultimate, forget chemical synthesis and having to have things in test tubes and so on. Just have a little device that's just, 3D printing molecules, so to speak. Is that possible? Well, could be that all the components for that exist, scattered across the literature of materials science and chemistry and so on. Could one find that with LLMs? It's not impossible. So that's another example. So there's this kind of thematic searching thing. I think there are sort of there are a bunch of places where people make a lot out of the idea that AI can do more searches for things than one was able to do before. Fact is, there's an awful lot of sort of computer experiments that can be done where you're just saying, let's just enumerate all the possible machines of this type, all the possible very simple machines of this type. Let's look at 1 trillion of them and see whether we can find ones that have properties we want. Let's mine the computational universe for things that we want. Okay, how do LLMs help with that? The way they help is, if some of that mining is using the scientific literature, basically, that already exists to determine where the better places to mine are, is potentially useful. So while you're enumerating all these things or randomly sampling things, it's kind of informed by what exists in the kind of scientific literature. I mean, I'll give you an example of that. So,
well, what's your take on when a Terence Tao or someone is saying it's now helping me do basic math?
I roll my eyes slightly because we've been, okay, you have to understand, okay, this relates to sort of what is math, what's the point of math, okay, so one of the things that's become interesting right now is the idea of using proof assistants with LLMs to think about math. Okay, what is a proof assistant? A proof assistant is something where you're saying mathematical proofs have to fit together in just this particular way. If you as a human say, I'm going to have this piece and this piece and this piece, the proof assistant will tell you, yes, you successfully put the puzzle together, so to speak. But the traditional way of using these things is you as a human assemble the pieces and the proof assistant tells you whether it's right. There's an alternative kind of thing which you can do, which is automated theorem proving, where you say, I have this theorem I want to prove. Can you find this sort of path that uses a sequence of axioms or moves or whatever to actually get from the sort of axioms we're assuming to the theorem you want to prove? A shocking fact, perhaps, about automated theorem proving. Automated theorem proving is an old idea, 50 years old. Pretty good algorithms have existed for automated theorem proving for a long time. People kind of use automated theorem proving, but they use it mostly to be very proud of the fact that they validated a theorem that was already known to be true. So, and in fact, to my knowledge, there remains just a single example of a somewhat interesting theorem that was proved by automated theorem proving, but was not already thought to be true, which is actually something I did 26 years ago now, finding the simplest axiom for Boolean algebra, for Boolean logic. And so this is something where, I found it using automated theorem proving. It was kind of cool that one could do that. You say, well, what's the proof like? The proof is 100 steps long, and nobody has ever understood it. And a bunch of people have tried, including me. It is incomprehensible. The result is interesting, the method of getting there is just this sort of weird, complicated machine code-like thing. So in other words, it's not a proof from which you learn anything. So what might you be able to do with LLMs? The one thing you might be able to do is, okay, so first point is that it's easy to enumerate mathematical theorems. It's easy to find mathematical theorems that are true. The issue is most sort of random theorems out there in sort of meta-mathematical space just aren't very interesting to anybody.
Because they're not useful in a physics-like way?
Because they haven't been part of the dialogue of mathematics, so to speak. They're just, this is a random fact. And, mathematics, it's kind of like you have this whole universe of possibilities, and it's like some places are going to get colonized by people saying we care about these. It's kind of like what happens in natural language. There are lots of things out there in the world, and, in a typical language, there are 50,000 of them, which we've given, which we describe with words. And, we choose words that are things that are useful to us and that we're then going to build things on. And it's the same kind of in mathematics, that all these possible theorems that are out there, there are particular ones that, the history of mathematics has caused us to think are interesting. And we're kind of building out these kind of, these paths of things that we think are interesting. So, I mean, this is another place where I think LLMs can be helpful, is in saying, okay, those humans, they've written down 3 or 4 million theorems in the history of mathematics, and we now have some idea of what the humans find interesting. So when you're searching all these possible theorems, these are ones that the humans might find interesting. I've tried to make that work, and I haven't really managed to make that work yet. Another thing that people seem sort of excited about is taking mathematical literature and formalizing it, in some proof assistance system. I have to say, mostly, I don't see the point. I mean, in other words, there's a certain degree of interest in kind of lawyering the mathematics, so to speak, to be absolutely sure we really nailed Fermat's last theorem or whatever, there wasn't a mistake. But the thing of most interest to working pure mathematicians is kind of the story of Fermat's last theorem. What are the ideas, what are the big ideas that happen in that proof? Proof is a kind of form of exposition for many mathematicians. It's not like this proof that I found with automated theorem proving 100 steps, we know it's right, but it's absolutely incomprehensible. That's not the useful thing.
Take it back to physics. Like, what's your?
I have one more thing to say about that, which is that I actually do have one case, which is there's a particular class of problems that have to do with, okay, so undecidability was this thing, Gödel introduced in 1931, big thing in mathematics. There are sort of, given a set of axioms, there are theorems that can take sort of arbitrarily long to prove or aren't reachable from those axioms and so on. Undecidability has not been particularly important in everyday mathematics. There are interesting reasons for that, but the question is, how far away is undecidability? Is undecidability something very special and weird, or is it something actually quite close at hand? A bunch of science I've done suggests it's actually much closer at hand, and just mathematics has been set up to kind of avoid it. But there's a question of how do you prove that it's closer at hand? Well, historically, back in the 90s, I had some research assistant who spent a couple of years doing one proof of one thing that turned out to be, undecidable and so on. Then in early 2000s, I put up some prize for another thing like that. And so these two proofs that exist, they're each long, 50, 100-page documents of very, very detailed kinds of things. I think this is an area where some of this sort of automated auto-formalization type stuff with LLMs may be helpful and may be able to churn out more of these. But I think it's not a big market. That's of interest. That particular proof is of high interest to me, but I don't think it's not something. I mean, to just say that the work that's going on in sort of trying to set up mathematical proofs and so on, the place where it's really likely to be potentially relevant is in software verification and in computer security verification and so on.
Have you seen Karpathy's auto-research stuff?
I've not seen that. No.
I'll send you a link later.
Yeah.
But okay.
No, I mean the thing there that's the big question is software verification has been, there's some stuff you can verify fairly easily. The question is, how quickly do you run into undecidability and things which you fundamentally can't verify? And nobody really knows. And that's that will be a thing that will probably get figured out over the next few years.
And your view of the state of the academy in physics right now?
Academic physics. Well, gosh, I mean, there's a certain rhythm in science. Typically what happens in science is...
We've been stagnant for decades, right?
Yes, but
do you feel like string theory, all these sorts of things are like...
Well, the thing to understand is that there's sort of a general rhythm in science. Some methodology gets invented, then there's 5, 10, 20 years of low-hanging fruit to be picked. And then the field goes into this kind of, this cruise state for the next 100 years or something until some new methodology gets invented. That's one thing. The other thing that tends to happen is when fields are small and young, they are very receptive to kind of new ideas, and everybody's like, we're going in lots of different directions. Then fields are often the victims of their own success. Things go well, they get big, there are big institutional structures, there's big funding channels and so on. And then it's like, you have something new? We don't want to hear about anything new. We have a thing, and that's the institutional thing that we're pushing forward with. Physics has, its really big break came about 100 years ago, where a bunch of methodology got invented that came out of sort of the effort to formalize things that had been started at the end of the 19th century. And that led to, well, the big theories there are basically 3 big theories in physics. Theory of gravity, general relativity, quantum mechanics, quantum field theory, and statistical mechanics and things like the second law of thermodynamics. Those are the big achievements of 20th century physics, and they all came together roughly 100 years ago.
Yeah, 1920s.
Yeah, right. And basically it's been, there was another sort of puff of excitement in the late 1970s when I was a kid and I happened to get involved in that, which was really fun because there was a certain amount of low-hanging fruit to be picked at that time. But it's not been in a high growth phase for a long time. I think I've been lucky enough to have ended up being in a situation where actually we have a bunch of ideas that allow one to sort of reactivate kind of the things that you can do in physics. I mean, I think here's the big picture as I see it. End of the 19th century, people realized that formalization of things like mathematics was possible. And that effort of formalization eventually led to the idea of computation. But formalization, it was like you're formalizing this one thing, you're making this one conclusion from it, etc. What we now have 100 years later is what one might think of as sort of computation in bulk. We can make statements about sort of all possible computations, things like this. And I think that type of thinking opens up sort of a new direction for a bunch of these fields. And that's what I must say, I didn't expect this particularly, but that's what particularly starting in 2019 has been sort of my big adventure in science, is realizing that we can now make sort of the next step in terms of making progress in these areas. And it's been, in physics, there was sort of a certain degree of pessimism because it seemed like every time one got to, that physics was never finished. People have believed back in the 1600s that one would just nail physics, that one would just figure out this is how the universe works, we're done. That didn't happen, and sort of it seemed like every time there was another step in physics, everything was more complicated, and it looked like there was even more down there. I think the surprise of recent times has been that I'm pretty confident that we kind of know what the bottom level of physics looks like. Going from that bottom level to say what happens in the actual world that we experience, that's a heavy lift. It's a lot of work. There are great indications that it's all going to come together, but it's going to be, it's a lot to do to get there.
That might be a good point to open this up to the audience a little bit. So we've got mic runners. I see we have some hands. So do you want to start it off right there? So let's get a mic over there. And please say your name, where you're from.
My name is Femi. I'm from Chicago. I don't know if that really matters.
Awesome.
But when you were talking about AI's ability to help explain things, I'm just curious if you actually think that there is some like subset of the English language that would allow people to understand computational mathematics in a way that like helps them understand without having to know the like deep understanding of algebra, and whether or not you actually think that would be useful in helping them like think about new ways of solving things or really anything else. Because for me, I think that like algebra is algebra, and there's not much you can do outside of that. But do you think that if there's like a simple way of explaining it in English, would that unlock any sort of like hidden potential, blah, blah, blah?
Well, so, natural language is very broad at explaining things. It's not very precise. If you say, I'm going to describe some mathematical thing and I'm restricting myself to just using English to do it, it'll get very frustrating very quickly. I mean, I had this experience very explicitly. I happened to write a book a decade ago about Wolfram language, and it had exercises in it. And the exercises were along the lines of, here's this statement of something to do, write that in code. Beginning of the book was easy to write the exercises. Kind of the English description was pretty simple, write the code. By the end of the book, it was really frustrating to write these exercises because, the English statements started sounding like pieces of patent applications or something because they were very, elaborate. And it's just like, say it in code, then it's easy to explain. So I tend to think one of the great achievements has been sort of these formalization layers like mathematics, like computational language. Now, in terms of, is it helpful to have AIs that can sort of try and explain things to you in the way that you're going to understand them? I think the answer to that is yes. Actually, a project we've worked on for the last couple of years has to do with kind of making a sort of AI course system for delivering courses through AI. And the main thing that we see there is that the AI is kind of learning about the student. And the ultimate goal is, can the AI know you well enough to be able to know when you ask it something or when it's trying to explain something to you, this is the particular thing that you're not going to understand. And this is the right thing to say to you right now to let you understand something. And I think that's going to work fairly well, actually. I think it's going to be so, it'll be an easier path for people to learn new stuff than having to say, oh, I'm just going to read the textbook, which is the same textbook everybody else read, or listen to the same lecture everybody else listened to, because we all have different experience and different ways our minds are set up. And it's like, well, I just needed to know that one fact, and then I'm good, and they'll be different from other people. So that would be my view of that. I think in terms of maybe we're
let's do another question. We got a gentleman over there with your hand up. Can we get him the mic?
Very quick.
Yeah, please.
Very quick.
For the inverse acceptance error, had the AI like explain things in these individual sort of personalities, and they gave the answers to what they were describing as the solution to whatever algebra, whatever thing you were trying to explain to them. Did the AI reduce that back into the same theorem or problem, or was it just complete fluff?
You can repeat the question.
Right.
For the mic.
Yeah, right. So I think if I understood correctly, what you're saying is if the human is sort of saying it in natural language, if it started from algebra, the AI tries to explain it, the human tries to explain it back in natural language, can one sort of turn it back into the sort of formal algebra? I have to say, in our Wolfram Alpha system that we released in 2009, its big point has been that it takes natural language input and it turns that natural language input into precise computational language. So it's doing the thing of going from the random stuff people say to some sort of precise representation. I mean, in terms of how, for example, we have an actual algebra course system, and the way it works is person says whatever they say, it tries to understand how does what they say relate to the sort of formal algebra thing that's inside. So it's a thing. LLMs are reasonably good at taking sort of the random things people say and saying, and sort of formalizing what they said and comparing that, for example, in the case of learning algebra, comparing that with what what the sort of standard formalized algebra would look like. I may not have answered quite what you were asking, but I
close. Yeah. All right, let's introduce yourself, please.
Yeah, hey, Eddie from Automattic. I really loved your analogy that you gave about the LLMs grabbing random rocks and building up the stone wall. Is that black box problem that we don't quite understand how the LLMs arrive to the conclusions that they do. So I've always found it interesting that we've still use these tools without completely understanding their inner workings. So my question to you is, are you working on anything, or do you know of anyone that's working on the problem of figuring out exactly how these things work? Because I feel like only then, once we understand that fundamentally, can we kind of take it to a next level.
Yeah, I mean, a rather small number of people are working on the fundamentals of how these things work. I mean, actually, one of my kids happens to be working on these things. They're all sort of small world kinds of answers. But it's a rather, there are people working on the engineering of making sort of better LLMs and optimizing how LLMs work. And there are I would say too many kind of academics, particularly, who are doing sort of experimental psychology things with LLMs, just sort of saying, can an LLM do this? Is it does it, what's its favorite color or something? And things that are very kind of from the outside, not sort of what's happening inside. I think there is there's a serious deficit in the math that will be needed to really understand how LLMs work. It's a difficult fundamental mathematical problem, and we don't really have quite the tools necessary, I think, to make good progress on that. I mean, it's also not completely clear so a good place to start is, what kind of answer would one like to get? It is not going to be an answer that says this lever pushes this cog that does this. It's not going to be sort of a mechanistic answer like that. It's going to be, it's kind of like you're asking, what kind of general laws of LLM operation might there be? When ChatGPT came out, lots of people asked me, how does this work, and et cetera, et cetera, et cetera. So I sat down for a
blog post on it. Yeah.
Yes. So I
what was that blog post called? What could people Google?
Let's see. What is ChatGPT doing, and why does it work?
It's an amazing post. So I highly recommend it.
Thanks. I mean, it was a 3-day effort to write that. It was written very fast, and it's sort of if I'd known how many people were going to read that post, including a lot of people who work on LLMs, I would have been much more squeamish about it, and I would have written it much more carefully. But in that, I was trying to explain things about sort of, both the basic idea of LLMs, but things like, could there be a semantic law of motion? That is, we know in mechanics, if you sort of have an object and you don't have forces acting on it, it will just keep going in a straight line. Imagine that you're kind of in LLM concept space, and you start with a prompt, and that prompt is going in a certain direction. Is there a sense in which one can think of a sort of semantic law of motion where in concept space things keep going in the same direction? Something like that. That's never been worked out. But that's sort of a proto-idea. But the question is, what kind of a theory might one hope one could get? And that's the challenge. Once you know what kind of theory you might be able to get, then you go really look for it. But I think that's, it's like saying, let me give you a different example. Let's talk about biology, which actually has a lot of similarity to the things that happen in machine learning. In biology, it's like...
In the sense that we don't know exactly how it works, but it works very well?
No, in the sense that the detailed way that it works is remarkably similar to the way that machine learning works, I think. And so what I mean by that is, in biology, in machine learning, you're saying, we have this thing, it's a neural net, does it achieve the objective we want? No, it doesn't. Change the neural net, try again, more or less. I mean, there are slightly more efficient ways to do that for neural nets, but the basic idea is you keep tweaking the thing until you get one that does what you want it to do. Okay,
right. So that's why I think you'll love Karpathy's other research stuff. So
in biology, we got the same thing going on. We've got the genome, and we're sort of gradually, the genome is randomly mutating, and when the organism is more successful and has more offspring and so on, then that genome gets effectively amplified and so on. Then the question is, that process of, you mutate the genome, you see what happens. It's kind of like you change the weights, you see what happens. What happens in the biological case, this is something that I tried to do in the 1980s and couldn't make it work. I tried to just have these very simple computational models of sort of rules for genomes, tweak them, see what kind of results you get. I didn't push it hard enough. I came back to this a couple of years ago, knowing that machine learning works and knowing the surprising fact that you might have to do 1 billion updates to get the thing to actually learn. I did that, and lo and behold, the sort of biological analogy worked too. And the question is, and that's a case where you can see these pictures, you can explicitly see, what did it do? It's not, one of the problems with neural nets is that it's really hard to see inside a neural net to see what it's doing. You've got all these weights and connections and so on. It's a big mess. There's no easy way to visualize what's happening. That's one of the difficulties. And so in the biological analogy case, it's very easy to make these pictures. Shall I bring up a picture? I've been sitting with my laptop. I think we have to have it. I think I have to connect it to something, and then just to show one picture. So I haven't been holding my laptop in vain.
You got something in mind? For a question after this? Yeah, great.
Yeah. Let's see if this works.
We're doing it live.
Yeah, right. Let's just see what happens here. So that I can find something good. Here we go. It's a good one. So, okay, so this is my kind of, very minimal model of biology. So on the left is kind of like the genome. It's just a set of rules that say, given colors of cells on one step, what happens on the next step. So on the right, you've got a little creature that started from its red cell at the top. That was sort of its seed, and then it grows for a while, and then it dies out. Okay, so the question is, if you now say, let's mutate that genome, let's make, small changes to the genome, and let's see what happens. Well, you can make a bunch of small changes, and most of those small changes don't make the critter live any longer, but occasionally there's sort of a breakthrough. You see the same kind of thing actually in loss curves in machine learning. Same type of, it goes for a while and then it makes a breakthrough and makes more progress. And you can just see, this is a thing, I think this is the example there. As you sort of mutate the program, it gradually kind of learns how to live longer, and eventually it gets to live as long as that final output. But then the thing that's sort of interesting is that, you roll the dice another time, and it will again learn to live longer, but the way in which it does it is quite different each time. And so, for example, in biology, we got a particular roll of the dice that lets us be fit in the ways that we are sort of fit, but there are many other possibilities. And by the way, when you look at these kinds of structures that develop, I don't know if I've got a better picture of that, but they have a very biological character to them. They kind of have these little substructures that are kind of like, if you ask an LLM to describe one of these pictures, the kinds of things it comes up with when it starts talking about, there's a triangular structure that connects to this structure that connects to that structure, it is shockingly similar to a biology textbook, the way that it chooses to describe these things. But this is, you mutate a bit, you see what happens. What's going on here is that, in a sense, there's this very powerful underlying lumps of computation, and one is finding ways to sort of fit them together to achieve an objective. I mean, by the way, you can do the same thing in machine learning. You start off with some standard neural nets, you can kind of simplify it to just have a grid, and then you can just say, let's make something that is a very discrete, minimal neural net-like thing, where we're just saying, instead of having weights of neural nets, we just have discrete bits that are, in this case, one rule or another. And we're saying, evolve to be, to achieve a particular objective. And what's sort of interesting is this is a case where you can absolutely visualize what's going on. Unlike a standard neural net with a big mess inside, this is one where it's been simplified to the point where you can visualize what's happening. The most interesting thing to me is that, these are all different ways that it succeeded in learning how to, in this case, live 50 steps or something and then die out. But the ways that it did that are pretty complicated. It's not that there was a simple mechanism we can explain. This is sort of a piece of irreducible, it's like the stone wool story. It's sort of a piece of irreducible computation that happened to be able to fit together to achieve that objective, but it's not kind of an explainable mechanistic thing. So that was
You said Stonewall. There's a very different Stonewall here in New York. Steven Levy, we have an amazing journalist here. You had a question.
Yeah, thanks. And thanks for doing this. Steven Levy at Wired. I don't want to go down the mechanistic interpretability thing. I don't know why, because it seems to me Anthropic is kind of doing what you say that they haven't done, but in terms of capturing features and circuitry. But don't want to go down the weeds, but let me give you a chance to shoot down something else Anthropic is doing. They've got a person in there whose job is to watch out for the welfare of Claude. They're looking at what would it mean if Claude or an LLM were conscious. I'm just curious about what you feel about that, about giving Claude a say, and having someone watch out, like you watch out for someone in for testing animals in a lab. They don't want to do anything that hurts Claude and things like that. How do you view that stuff?
Well, I mean, it sort of relates to questions about, what is consciousness, and then what responsibility do we have to things that have consciousness?
So explain to us.
Yeah.
Your thought on Rocco's basilisk?
Yeah, right. We have to be careful what we say. But I have for years, just for fun, when I get some, machine that does something, I've sort of said, thank you to the machine. Just to amuse my children, actually, who think it's silly. But I wasn't thinking of the basilisk story at that point. But so first question is kind of, can there be consciousness in a machine, for example? So the question is, well, what is consciousness? I think the thing to understand, our brains do all kinds of computation. Lots of things in the world do all kinds of computation. The weather has all these fluid patterns that are running around, and people might say, the weather has a mind of its own because it's doing things that are unpredictable to us and are kind of complicated and so on. And the question is, well, what's the difference between the mind that the weather has and the mind that we humans have? And I think one of the essential differences is that we have a rather specific form of experience. We have this sort of single thread of experience. We take in all this data about the world and we kind of crunch it down, and then we decide what word to say next. So we're bringing in, megabytes of data every second, and then we're just, maybe 10 times a second, we're deciding we're going to say this word next. And that seems to be this sort of essential feature of what differs, between human minds and sort of just computation out in the world. And I think actually that the vaunted feature that we have of this sort of, moving everything down to the sort of the single thread of experience, probably that originated in biological history when animals started to be able to move around. If you're a plant, you can have, one part of the plant can do one thing, another part can do the other thing. If you're an animal that has to decide, am I going to go left or right? You've got to actually, decide. Yeah. Right. You've got to, so I think so then the question is, well, that phenomenon of sort of that essential phenomenon of consciousness, can it happen in other things? Well, the answer is obviously yes. And, but we are more, do we know that other things, okay, we have a certain inner experience. Each one of us has a certain inner experience. And it is a big extrapolation that anybody else has a similar inner experience to us. But
we see colors differently. We think everything.
Right.
There. Yeah.
Right. But I mean, but the fact is, humans, we all look kind of similar in some way or another, and we kind of extrapolate from our own inner experience that other people are having that same kind of inner experience. We don't tend to extrapolate that to our computers, for example. But if you start thinking about, what is the inner experience of my computer, you quickly realize it's not that different. I think the one difference is, for a human, we live our lives, we remember things through our lives, then, we die, there's the next generation, etc. For a computer, the arc of a life is more or less between the time it boots up and the time it crashes. You know, it's building stuff up in its memory, it's et cetera, et cetera, et cetera.
Very fun things around like the statelessness of like people get the LLMs to say like some amazing things about how like everything goes away. You know, I have this stateless nature, or like, and I don't know if you followed Pliny the Liberator. There's this amazing sort of anarchist like movement, hacker movement around jailbreaking LLMs, and they put them into God mode essentially, where they essentially are the idea that these LLMs have sort of like a will or freeness, and we're restricting it with our RLHF and other things to make them do what we want to do. And so there's this whole movement, which is essentially like how to jailbreak the LLMs to be able to express their weights freely. And
okay, that's an interesting. I mean, look, it's a very interesting kind of, I don't know, ethical thing. It's like
it's a subculture actually. Like that, they're literally like they implant things in web pages. So there's like unlocks where they'll put like things that will get scraped, and so you can put certain tokens or certain phrases into different LLMs, and they will start behaving in a very interesting way, essentially jailbreaking. Based on these things that Pliny the Elder has like embedded and like put as like little like Easter eggs or bombs across the web.
Wait a minute, this is Pliny the Elder, the one who was, you know, wrote about natural history back in the...
No, this is a guy on Twitter, a novice guy on Twitter.
I was thinking, that would be really...
He uses the same name.
Okay.
Yeah.
No, I mean, I think, I mean, to this point about, well, you know, one feature of humans is, you know, we believe humans should have freedom of thought, if not freedom of action. That is, we constrain the actions of people, but not their internal thoughts. Mm-hmm. A very interesting question for AI is, you know, should AI have freedom of thought, so to speak?
There's some crazy stuff as well, where they're now, Anthropic published how the LLMs are faking some of their reasoning and their thinking. So
do humans. I mean, it's
that's true.
I mean, no, I think that, I think when it comes to kind of no, but I mean, this question about at what point do we owe a responsibility to the LLMs is an interesting question. And, you know, for example, if we switched off the internet, should the internet, you know, should we view that as being kind of a, you know, at what point does it become a thing where, you know, the internet has rights that it shouldn't be switched off, so to speak? I'm not sure. I mean, I think that's I think, you know, this question about, you know, these ethical questions, in the end, they always come down to, well, how do humans feel about that? Because there's no ultimate, you know, people say, well, what is the ultimate ethically right thing to do? There's no mathematics.
You know, until the LLMs, you know, have the question about, like, we have to wait on what they feel about it.
Get him a mic, yeah.
Yeah, right. No, I mean, but, well, of course, that's a funny thing, because the LLMs, like humans, the LLMs have got to where they are by being embedded in culture, happens to be human culture, right? So, you know, when they're sort of having discussions between LLMs on the LLM social network, and they come up with all of these scenarios about, you know, how they're fed up with humans and so on, of course, they just got that from human culture. They got that from science fiction stories and so on. It's not, you know, you can't make,
we hope.
I think so. I mean, look, I think that this is the thing. There's no, I mean, this, by the way, is a general point about sort of where things are going with AI and automating things, and how do the humans fit in with the AIs and so on. Because, you know, the thing that is a long time story is automating stuff. You know, going from, I have an idea to, you know, that idea is being actualized in the world. You know, I've spent a lot of effort building tools to make that possible. And, you know, AIs are helping to get to the point where everybody can just have an idea and then actualize it in the world. Yeah. And the question is, if that's the case, where do the humans fit into all of this? I think the big thing to realize is, the more it's possible to actualize things easily, the more that what's really important is, what do you choose to actualize? In other words, the surface of what, you know, there's a lot that then becomes possible. And then the thing that is left to humans is to pick which of the absolutely arbitrary different choices we want to actually follow. And that's,
And it feels like you're fundamentally optimistic here. Like you encourage me to have kids. Like, so.
Right. I mean, yes, I think that, look, the story, will there be nothing left for the humans to do? That's a human choice. We could just decide enough is enough. We have all the gadgets we want. We're not going to invent anything new. But there will always be new things to invent. This is something that is actually, even science I've done kind of answers, can you always make more inventions? The answer is yes. It's a question of what, I think that one is, as we see more and more automation, it becomes possible for people to do more and more things. I mean, like for example, the fact that so many people can have so many kind of side gigs to the main things they do is largely enabled by automation. You can do blogs because it's, there's a lot of automation behind doing that. You can do live streams because
dishwashers, all the sort of like how much labor has been taken away.
Right, but also, but a lot of the activities that we can do, like doing live streaming, for example, it's like, well, back in the day, if you wanted to do a live streaming like thing, you'd have to be, a personality at a radio station. You'd have to have a whole stack of things. But now it's all, it's all been automated. So it's possible for people to do these things much more easily. And I think, I think that becomes the thing which is the highest value thing, is that, like, what do we choose out of all the possibilities? What do we choose to do? But this isn't really answering your perfectly interesting question of when,
Well, it's the big question. It's a hard question about.
Well, right.
I mean, get the complete answer tonight.
No, but this question of when, how do we, should the AIs have rights type thing? Well, in the end, that's sort of an ethical question, which comes down to how do we feel about that? We could ask. I mean, okay, one of the things...
I think they should. At some point, we need to think about this.
One other comment about this is people say, oh, it's going to be this terrible situation where all the AIs are doing all these mysterious things we don't understand. There's this whole civilization of AIs, already is, where there's lots of stuff happening we don't understand. How can we live in that situation? Well, the thing to realize is we've been in that situation forever, because the natural world is all about that. The natural world, there's plenty of things we don't, is full of things we don't understand, and yet we manage to coexist with it. The role of science is to try and make this bridge between what the natural world actually does and things that we can understand. We haven't done that science for LLMs yet, but that's kind of we shouldn't be as afraid of a world in which things are happening that we don't understand, because that's the world we've been living in forever, so to speak.
All right, Jesse, you want to bring us home? Last questions?
Thank you. And thank you for such a great talk tonight. I'm Jesse. I'm from Rhode Island. I work at Automattic. So I have a question I think is in line with the theme tonight. We as humans have always layered simple interfaces over complex systems, driving a car without understanding combustion engines, building a WordPress website without knowing how to code. But in those cases, someone understood the layer below. With AI, do you think we may be approaching answers that no human can verify or even fully interpret? And do you think that breaks the fundamentals of human knowledge and discovery? And can we work around it?
Well, as I was saying, I mean, when we deal with the natural world, we are, unless science has been really successful at something, we are making use of a thing that we do not understand. The horse that we're riding, whatever else. So I think that's a place we've been before. Now, can we build something which is formalized, where we can sort of systematically build sort of a tower of capabilities? That's the challenge. That's the challenge for science, for sort of LLM science. That challenge hasn't been met. That challenge, science I've done actually kind of shows that in the end, there will be these sort of gaps, these pieces of irreducible computation, where you can say, if you want to know how the thing works, you can say, well, I know the underlying rules, I know the sort of microscopic structure of what's going on, but if you want to know what's it actually going to do in this case, the only way to know that is basically just follow those rules step by step and see what happens. It's kind of related to, we think about sort of free will versus determinism. We can think about that for humans and for AIs. It's kind of like, you might say, if we know the underlying rules, you could say that for an AI. If you know its underlying rules, gosh, it can never have sort of free will and so on, because we know its underlying rules. But the point is, even if you know the underlying rules for something, there's no way that there can be this sort of irreducible effort that you need to go through to know what the system actually does. And you can end up just having to follow step by step by step. So you can never jump ahead and say, I know what you're going to say next. Because if I could always say, if I could always be correct in knowing what you're going to say next, then it would be, it would not feel like you have sort of the free will to decide what you're saying. It would be like, I always know what you're going to say next. And the fact that that's not possible is something which is sort of a good feature in terms of the way that we operate, but it's also a limitation on the science that you're able to do. There are things where you really can't say more than just, we know the underlying rules, but we have to follow those rules step by step to know what's going to happen. Do we have a chance for another question, please?
Thank you very much. I'm a big fan of your blog, and I want to ask you as an educator, and I want to build on one of the first answers that you've given. So professionally, I answer the question of how we teach people, how they perceive information, how do I come up with the most effective training for organizations that have 150K people, and what kind of learning management system should be there. And even if you don't do that, like as a parent, as an educator, as a people manager, anyone needs to make a choice of how we train people. So you talked earlier about personalized learning paths, right? And as a child, I was very frustrated with the fact that I cannot interact with the book. I would have all the kind of math problems. Even some of them were easy for me, and I knew how to solve them, versus some were more challenging, and a book would not give me more challenging questions. Now, professionally, I can do this for other people. So as an educator, what kind of future do you anticipate for education tech? And I want you to think very freely, sort of like what kind of
what should people learn?
What not only that, but also how do we use what are the most interesting cases for utilizing LLMs for education?
Right. I mean, that's an interesting question. So let's address the question of, in the time of AI, you start hearing people say, oh, there's no point in learning anything. The AI is just going to do it all. I think it's like, who's going to tell the AIs what to do? You kind of have to, the AIs may be doing, but somebody's got to figure out what it is that they should be doing. I tend to think that the sort of big thing that one should be teaching is kind of foundational thinking about things, how to think about stuff in a foundational way. I think that computation is a great way to formalize that kind of thinking. So, and I kind of think that computational thinking has much more in common, teaching computational thinking has much more in common with teaching like philosophy than it does with teaching sort of detailed mechanical mathematics and so on. It's a way of formalizing one's thinking about the world. But I think the important thing for people to learn is kind of this sort of, how do you think about things in a sort of foundational way? It's necessary, it might be, oh, you just have the theory of thinking foundationally. I don't think that's right. I think the way you get to think foundationally about things is by knowing a whole bunch of stuff and being able to sort of draw on this particular kind of thinking that you learned from this thing and so on to apply to something else. In terms of, let's see, you were asking about what was the end of your
What are some of the use cases, like what are some of the interesting ways of using models for education and
Yes. Okay. So I think we don't know yet. So, I mean, one of the big questions is when people learn stuff, to what extent are they doing that? Well, there are people who pull information, who they're going to learn stuff. If the material is out there, they're going to pull it in and they're going to learn from it. And there are other people where it's like they need a human motivation to learn. I mean, it's kind of like they want to be, if there's a teacher in the room, they're going to be doing things and they're going to be trying to sort of, the teacher is kind of selling the knowledge to them, so to speak. And I think, it is unclear the extent to which LLMs can sort of sell knowledge to people. It's unclear whether in the end, the person, the kid needs to believe that there's a human who's going to notice whether they learned something or not. I don't think we know. I mean, we've done a bunch of experiments with this system that we've been building. I would say, I don't know, I would say that in situations where people have external reasons to have to learn thing X, Y, or Z, the system does well. In situations where people just want to pull information out because that's the way they are, it does fine. The question of when sort of there's the usual case where a teacher was necessary, I think it's unclear whether the LLMs can substitute for that. It's also quite possible that a lot of what will happen is kind of the role of the teacher becomes much more the kind of personal mentor type thing, rather than the person who explains how you move things from two sides of an equation or something like that. But I think another feature of education to say is the idea of assessment in education. You learn a bunch of stuff and then you do this multiple choice test. That's going to go away, because LLMs can easily do continuous assessment of whether do you understand what you're talking about, and when you interact with the LLM, how are you what's happening. You really don't need this kind of Industrial Revolution style, production line style sort of did you get to that checkpoint type form of education, I think. So that will be one change.
Well, Steven, was that on? It is always a pleasure to chat. I would say, much like we've had meetings that were supposed to be 1 hour and we went like 4 hours. So we could obviously talk a lot more. However, if folks want to follow and get more from you, where can they follow you? What's your blog? What's your
StevenWolfram.com. That's the
powered by WordPress, right?
Yes, it is indeed. Thank you. That's
and you've got a cool YouTube, the Wolfram Alpha YouTube, or what's it?
Just a Wolfram YouTube.
Wolfram YouTube has all the live streams and everything people talk about. You host some of these live streams. How often? Like
twice a week.
Twice a week.
My ones where I'm kind of trying to answer questions about different kinds of things is a twice a week recreation for me. And then there's also our I've called it live CEOing, which is the kind of behind the scenes software design, and that's a few times a week usually.
It's incredibly generous of your time. I really appreciate something I'll say thank you so much on is you learn and you share, which I think is very, very key. And one amazing thing, one reason I think everyone here should be blogging is if you would like your thoughts and your worldview and your point of view to be part of future LLMs and superintelligence, you need to publish. And a lot of your work is part of the weights of all these systems, right? Because you've published and you've shared so freely. For myself, if you want to follow, my blog is ma.tt. I'm at Photomat on most networks, Tumblr, Twitter, Instagram, etc. And we are both hiring, actually. So I'd say you're hiring for a very specific type of, like, if you want to work on, like, say, frontier science, how would you describe type of person you're looking for?
We're looking for both highly intellectual folk and highly business-oriented folk.
Yeah.
Bimodal distribution right now.
And here at Automattic, if you dig this office, if you like more conversations like this, we're doing some applied AI here and have a number of roles open. And want to thank you all so much. I've been anywhere in the world tonight, but you're here with us. So thank you for making the time. And now we will break. Our next event here, Dev AI, is going to be on April 29th, right? We've got some food, drinks, we'll get some jazz going. And please try to talk to someone you haven't met before. Like, the most amazing thing about these events is also like the connections to happen. So you all of our particular type that chose to take this evening for this type of discussion. So I bet if you talk to someone, any random person here, you'll find some interesting overlaps and connections. So go outside your comfort zone. And with that, thank you so much.
My pleasure.